Welcome to this explainer, the invisible engine, unlocking the solar grid puzzle. So today we're stepping behind the curtain to investigate the totally invisible, high-stakes engineering required to run a renewable power grid. We see these towering wind turbines and shiny solar panels and kind of just think, great, the job is done. But generating the power, that's literally only half the battle. Getting it to play nicely with a grid designed over a century ago, well, that is a massive software-driven puzzle. Let's get right into it.
To really understand why this is such a puzzle, we actually need to go back to June 4, 2022 in Odessa, Texas. On that day, this tiny piece of equipment called a lightning arrestor failed at a power plant. It was just a fairly typical short circuit, the kind of fault that happens from time to time. But what followed was anything but typical. Within seconds of that one little short circuit, the entire Texas grid unexpectedly lost 2,500 megawatts of generation capacity. To put that into perspective, that is roughly 5% of total demand just wiped out in a flash. The system frequency plummeted to a dangerous 59.7 hertz, and that sent absolute alarm bells ringing through the whole power industry, because it nearly triggered a full-blown emergency where customers would actually have to be disconnected.
But honestly, the craziest part about this massive drop? It happened just before noon on a perfectly sunny summer day. Solar plants spread all throughout the state were at peak output, pumping out about 16% of Texas's total power. But the investigation into this 2,500 megawatt loss revealed something pretty shocking. It was entirely a software reaction, not a hardware failure. That's right, it wasn't a physical equipment failure that caused the solar plants to drop offline. The panels absolutely didn't break. Instead, a wide variety of algorithms and configuration settings in the power conversion equipment reacted in highly unexpected ways when they sensed that initial, really minor disturbance.
Which leads us to the ultimate question. Why did a small electrical fault cause a massive solar blackout on a perfectly sunny day? It's a great question. So let's dive into this by peeling back the layers of the fundamental engineering mechanics governing how renewable energy actually connects to our legacy power systems. Basically, the answer lies in a massive clash between old and new technologies. Direct current, or DC, versus alternating current, or AC. It all starts right here, with this fundamental clash. Solar panels and batteries output constant direct current, but our legacy bulk power grid relies on the wavy, oscillating waves of alternating current. Bridging that gap is exactly where things get complicated. We're essentially trying to force two fundamentally different electrical languages to seamlessly communicate in real time. So because the grid speaks AC and solar panels speak DC, we need a translator, and a highly stressed one at that. This brings us to inverter-based resources, or IBRs for short. This is the industry term for energy sources like batteries, solar panels, and most wind turbines. Why? Because they absolutely require an inverter to bridge the gap between the raw DC output and the grid's wavy AC requirement. They don't just naturally sync up to the grid like a big traditional coal plant would.
Now, decades ago, the oldest inverters were just these clunky, inefficient mechanical devices, basically a DC motor spinning an AC generator. But today, most modern inverters use solid-state electronic circuits. They rely on this incredibly clever technique called pulse width modulation. Essentially, rapid digital switches inside the inverter turn on and off at absolutely blistering speeds, creating these really rapid, choppy pulses of power. By precisely controlling the timing and the width of these pulses and passing them through filters, the inverter smoothly transforms that chopped-up DC power into an approximate AC sine wave.
But creating an AC wave isn't quite enough. So how do we get solar power precisely onto an AC grid without causing catastrophic electrical damage? I mean, you can't just plug it in and hope for the best. A grid tie inverter has to perfectly synchronize with the phase and frequency of the grid. It does this using a circuit called a phase-locked loop. Basically, the inverter constantly senses the voltage of the larger grid and times all of those little digital switches to flawlessly match exactly what it sees.
But here's the catch. Grid-following inverters only work when the grid is already up. This is a crucial point. These standard solar and battery setups are what we call grid-following inverters, and that introduces a massive limitation, right? They only work when the grid is already humming along. They completely lack what engineers call black start capability, because they need an existing AC wave to lock onto and follow. If the grid goes down, your grid-following solar panels go down right along with it. It literally does not matter how sunny it is outside. Without the grid's heartbeat to follow, they are completely blind. This is actually exactly why your rooftop solar won't keep your lights on during a neighborhood blackout, unless you've got special islanding equipment installed.
And, synchronization isn't the only complex job these devices handle. Let's break down how resistance, voltage, current, and total power output relate to each other. The power output from a solar panel is not a simple straight line. Because power is simply voltage multiplied by current, there is a specific resistance sweet spot right in the middle where those two numbers multiply to create the absolute maximum total power output. If you lower the electrical resistance, the voltage goes down, but the current goes up. Deviate even slightly in either direction away from that exact resistance sweet spot, and you are leaving available energy on the table. To solve this, large solar installations use a maximum power point tracker, or MPPT. This is a genuinely crucial algorithm, usually housed right in the inverter, that constantly adjusts the resistance to follow that exact peak power point. And let me tell you, this is a moving target. The optimum resistance shifts dynamically throughout the whole day, depending on the exact temperature of the panel and the amount of cloud cover passing overhead. The MPPT is just continuously hunting for that peak to squeeze every last drop of capacity out of the system.
Squeezing out that capacity is absolutely vital because of our next major challenge: grid frequency. You can think of frequency as the critical heartbeat of the power grid. It is the exact, real-time measure of the balance between generation and demand. If we all get home and turn on our air conditioners and demand outstrips the power supply, the frequency of the grid literally slows down. If it deviates too far, motors overheat, equipment malfunctions, and the grid operator is forced to start cutting power to customers to save the system.
Let's see how this builds into a highly stressful split-second sequence during a grid failure. Step 1. A massive generator trips offline unexpectedly. Step 2. Instantly, demand exceeds the remaining supply. Step 3. The grid frequency begins dropping like a rock. And finally, Step 4. The nadir is reached. Operators now have a terrifyingly short window to inject more power into the system before that frequency hits that critical low point, the nadir. If the nadir drops too low, bam, cascading blackouts. The entire game comes down to the slope of that drop. How fast the frequency is falling dictates exactly how many milliseconds operators have to react. This highlights exactly why transitioning to renewables completely changes the physics of the grid. Let's look at thermal plants with physical inertia versus inverter-based resources with no physical inertia. Traditional thermal plants, like your coal or natural gas plants, are massive spinning physical machines. They act as gigantic synchronized flywheels. If a fault happens, their sheer kinetic energy keeps them spinning, naturally slowing down that drop in frequency we just talked about. They provide physical inertia. Inverter-based resources, however, they're just solid-state electronics. They have absolutely zero physical inertia to help arrest a grid deviation. With more solar and less spinning metal, the slope of a frequency drop becomes much, much steeper.
Primary frequency response, leaving money on the table. To combat this lack of physical inertia, grid operators require inverter-based resources to provide primary frequency response. Since they can't rely on a spinning flywheel, solar and battery plants must instantly inject power digitally during an under-frequency event. But here's the rub: you can't inject power you don't have. This forces these plants to intentionally run below their maximum capacity just to maintain expensive energy reserves. So for power companies, holding back generation capacity simply to stabilize the grid literally means leaving money on the table.
Aside from injecting power, these inverters also have to survive the extreme chaos of a fault. This is called ride-through. And man, it is an incredibly delicate, high-stakes tug of war. On one hand, inverters absolutely must have hyper-fast protective software systems to de-energize and prevent really expensive equipment damage during a voltage spike. But on the other hand, grid operators desperately need them not to be so sensitive that they trip offline during a minor, momentary glitch. If they pull too hard in the self-protection direction and all trip at once, well, it leads to a cascading outage, which, bringing it all back, is exactly what caused that massive 2,500 megawatt loss in Odessa.
We're looking at the growing pains of inverter-based resources. Things like a lack of black startability, low physical inertia, and extreme sensitivity to faults. What we are experiencing right now are basically the growing pains of a massive technological transition. We are awkwardly forcing digital, inverter-based resources to play nicely with an aging analog power grid. The core engineering hurdles are stark, right? We've got that lack of black startability, dangerously low physical inertia, and an extreme software sensitivity to grid faults. And on top of all that, every manufacturer has their own flavor of code and protective settings, making grid-wide coordination incredibly complex.
But hey, there is an incredibly promising future on the horizon, and this is where it gets really exciting. Enter grid-forming inverters. Unlike the grid-following models that need an existing heartbeat to function, these advanced grid-forming inverters generate their own. It's wild. They can actually provide synthetic inertia, mimicking the physical response of a massive spinning turbine.
Even better, they can block start the grid from a dead stop and support isolated electrical islands without ever needing an existing AC wave to follow.
We are building a more reliable, sustainable, and resilient grid. Because these new inverters are completely unconstrained by physical, mechanical limitations, they represent a monumental leap forward. They can chop up and distribute power basically however we want them to, delivering a sustained response that a physical flywheel simply cannot match. Engineers all across the industry are rapidly solving the software bugs that caused the Odessa incident. They are turning a fragile mix of old and new tech into a vastly superior, more reliable, sustainable, and resilient power system.
The grid is no longer just a physical machine, It's quickly becoming a massive computer. And that leaves us with a fascinating yet slightly chilling thought. As we rebuild the massive kinetic machine that powers our world entirely in code and silicon, solving the physical limitations of the past, what invisible, software-driven vulnerabilities are we creating next? As we rebuild the massive kinetic machine that powers our world entirely in code and silicon, what invisible vulnerabilities are we creating next? Thanks so much for joining me for this explainer, and remember to keep questioning the invisible infrastructure all around you.